Welcome to the demo on Node2vec risk analysis for cyber-physical systems. Our first step is to create a cyber-physical graph using the WSCC 9-bus system as an example. Here's a one-line diagram for our 9-bus system, which has 3 substations colored in yellow, purple, and blue. Each substation contains its own generator, buses, and loads. We also create a cyber topology which is composed of relays, HMI, and etc. The control center is supervised 3 substation status. To integrate the physical and cyber networks, we consider the relays as cyber-physical component that interconnect 2 layers. Each component of the system, including the buses, relays, and Internet switches, will be represented as nodes, while the connection between them will be represented as edges. After combining, the cyber-physical graph helps us know the interaction between the physical infrastructure and cyber infrastructure, just as shown in this 3D graph model. Suppose we detect an intruder targeting the cyber-physical graph. This could be an attacker attempting to disrupt the system operation, compromise sensitive data, or cause physical damage to components. To detect intrusions, we can leverage various techniques such as anomaly detection, snort, and so on. So the question is, what kind of technique should we apply to access the risk levels as well as the risk scores, and how should we mitigate the risks before it getting more severe? Node2vec is a powerful algorithm that learns continuous feature representation of nodes in a graph. It works by generating random walks on a graph and then optimizing a model to predict the likelihood of various nodes based on this walk. In our cyber-physical graph, we assign the common vulnerability scoring system access complexity metric to the edge weights. So edges connecting nodes in the graph are weighted based on the complexity of access. In this 3D model, we can see that the first target is substation A's Ethernet switch 1, following by substation A's second Ethernet switch, relay 21, B5, and etc. The sequence generated by random walks are transformed into node embeddings. These embeddings encode the structural information of the graph, emphasizing the likelihood of nodes that are likely to occur in the random walks. Nodes that are likely to be visited are encoded with similar embeddings, reflecting their topology closeness in the graph. And now, let's turn our attention to the analysis result table displayed on the screen. This table provides a comprehensive overview of our findings, with various metrics and classification for each node in the CPS graph. Cosine similarity represents the likelihood of each node being targeted or attacked within the CPS graph. Nodes with higher cosine similarity scores are more similar to the nodes that have been previously targeted or compromised. In addition to cosine similarity, we have various impact metrics to compute the final risk score for each node in the graph. By carefully analyzing these metrics, we can identify critical nodes that may be potential targets for intrusion, as well as access the overall resilience of the system. And finally, by leveraging visualization technique, we can effectively compute and evaluate risk assessment to strengthen the security. Figure 6a provides an overview of distribution of risk scores across the nodes. Nodes are characterized based on their risk levels, with most nodes falling into lower risk range. In Figure 6b, highlight the high-risk nodes within the CPS graph, which are in red, while nodes within lower risk are represented in olive. This visualization enables us to pinpoint nodes that require immediate action and mitigations. Figure 6c represent a scatter plot that visualizes nodes based on their likelihood scores and impact scores. Nodes with higher likelihood score and impact score are positioned toward the upper right corner of the plot. By examining this scatter plot, we can identify nodes that pose a significant risk being targeted and access the effectiveness of our mitigation efforts in reducing their risk levels.